the continuous version of the problem we studied first. See, we studied discrete observations. Signal is present or signal is not present. I mean, of course, plus noise, plus noise. And another prop. So remember, these are continuous versions. So this, to deal with this, so you collect the data. Look at here. It is not discrete observation. You collect the data. So you collect the data over some time.
Professor, I can't see that.
Yeah. I am. The lecture is going to start only in few minutes. So all I won't write below this, right? So all this says is that you collect the data. It could be either this or this. But because it is a continuous time, we need to develop some tool. So this is very similar to what we discussed in lecture 1, right? So this is, we will also address this as we move along. So remember, because of all this funny alignment, see whether you can switch on this. I don't think so. But, yeah, that's good. So because of the rescheduling the exams, the coursework, you are supposed to have been exposed to this in the previous lecture. Now, I know this is transition time, so I am actually going to quickly go over through the fundamentals also, but maybe in a, remember we used to have just a course on stochastic processes. Essentially, I am going to cover the whole thing, but in the remaining 7 weeks. So you get 2 courses for your money, right? And maybe after 3, I think including today, we have 7 more lectures. So sometime in the 5th lecture or 6th lecture, we will be able to attack that problem. Okay. Now you're going to see a lot of interesting material. Again, it is up to you how much you want to get involved with all this stuff. And so let me start with the definition, and I'll probably go over a few examples, etc. So a stochastic process is a collection of waveforms or realizations. There are 2 variables. This is the random phenomenon. The other one is what you are familiar with, the time. So the simplest one is you toss a coin. If you get head, you can think of one waveform as the output. If you get tail, you can realize it as another waveform. Or you have complex natural phenomenon where nature throws the dice, multi-phase dice, and depending on the outcome, a realization comes up. So you can think of the noise phenomenon in that manner, because even at the same place, if you do, if 2 people measure the noise, it's because of the complexity of the underlying phenomenon, no one is going to come up with the same waveform, right? Because nature keeps throwing dices, and depending on the outcome. So the best thing you can describe this whole process is using this entire collection of waveforms rather than one specific waveform. So we have to study the properties of this process, keeping in mind that you're looking at this big picture. Each of them are called a specific realization of the process. And so the collection represents stochastic process. So the question is, how do we I think in this, how do we characterize this? Okay. So the key instant is that if you freeze time and look in this direction, remember, you're fixing time and looking in, so two variables, right? It's like a second, one variable is the various random outputs. So this definitely depends on the experiments. In other words, even if you fly two planes into a turbulent region and make measurements, it's not going to be identical, right? Because of the complex nature of the turbulence, depending on where you measure, you may get one realization, other realization. But you can imagine if you have 10,000 different airplanes there making the same measurements, or 10,000 sensors, they are going to give you 10,000 waveforms, and the waveforms together represent that turbulence, and then whatever you want to study, you study it from that, all of them. That's why you put sensors everywhere, and you have to, so these are the sensor, each sensor output is possibly representing one specific realization, right? And you have to look at this totality of realizations and see what you can predict, what you can figure out, right? So if you fix time, you see, I see one realization, one snapshot, etc. So then this just looks like a random variable. A random variable is, depending on the nature of the experiment, you get a value, or nature of the random outcome. If it is head, you get 1. If it is tail, you get -1. Right? So the one way to fix the stochastic process is that if you fix time, what you see is a random variable. Of course, here I fixed the time to be t1. If I fix the time to t2, I get another random variable. So I can call this random variable x of t1. This is x of t2. So x is actually like this, right? So only t1 is fixed, and generally we, for notational convenience, we write it like this. That means when you fix a t1, it's still a function of psi. Depending on the value of psi, it could be this, etc. And that's what we mean by a random variable, right? When you do an experiment, the outcome is uncertain. Each of these values happen either with the specific probability, or this, if it's also possible this psi could be continuous, in which case you will have as you know, each random variable will have a density function or discrete function. Depending on the nature of this, that density function or discrete will be either discrete or continuous. So if you have a random variable, it has its own density function or distribution function. This is another random variable, it has its own density function or distribution. Now you can say that if I have two random variables, there are two possibilities. Either they are independent or they are dependent. So we can begin to study the dependency between sense. Of course, if it is coming from the same natural phenomenon, then most of the time it's reasonable to assume that this and this has some dependence, and we would like to know what that dependence is. So remember, a random variable can be described using its density function. If you have two random variables, they have their own density functions, but you also can begin to talk about their joint density functions. Then of course you can bring in more time instants, t3, tn, etc. Now you have n random variables, and you have their, so each random variable has its own density function, right? And a distribution function, right? So remember, if a random variable x, generally it is a function of x. But because this random variable x1 is corresponding to time t instant, it's reasonable to assume that this density function, or whatever is here, may be peculiar to that specific time instant. It may not be, but it is possible. Similarly, the density function here, remember it's a random variable here. So a random variable has its own density function. You don't have to start assuming that these two density functions are equal. That's what this says, right? So T2 will be a different random variable x2, but it is a different time instant. So this function could be different from here or could be the same, and it has its own distribution function also. Of course, you may say, why did I use x here? You can use x1 and x2 also. You can use any variable. In any case, you know that this is a dummy variable, right? This is not a variable. The density function is in terms of x. This is just to show that this density function actually corresponds to time instant t2. Hello? Right? If you don't like t2 here, you can write it here. Somewhere you need to bring the, make a notation that this is a function of t2. But the variable here is x. So if you consider, remember, if you consider two random variables, you can also think of their joint density functions, right? So that will be in general like this. You have two variables x and y, or x1 and x2, but the x1 corresponds to time instant t1, x2 corresponds to time instant t2. And if you have many of them, you also have their joint density function, right? x1, etc., xn, x1, x2, etc., xn, t1, t2, etc., t. So you can go on like this. So this is the way to describe the complete picture. That is, you take time instants t1, t2, etc., tn. For each time instant, you have a density function. Considering two of them, considering xi and xj, you have xi comma xj. Then you can consider three of them, four of them, etc. Ultimately, all of them together gives you the joint density function. This should be, you can do this for any number of n and so on, right? So this is called the first order, this is called the first order characterization of the process. And of course, similarly, this will be the second order characterization or description. This is the nth order characterization and so on. Nth order description. So question is, how do you describe a stochastic process? Remember, it's, if the variables are continuous, then you fix a certain arbitrary time instance. Anywhere you put your hand, you fix t1 through tn. Compared to those t1 through tn, you generate n random variables. They have all these density functions. So you can keep doing this for all orders. So you can see it is messy, but nevertheless, this gives you, if you have knowledge of all these functions, it gives you complete description of the stochastic process. Then we back off and say this is too much, right? Who has the time and energy to find all these functions? So we'll probably go and study here. So mostly we'll use the first order characterization and the second order characterization of a stochastic process. Remember, the first order, if you have a density function, of course you can think of its mean. If you have the joint density function, you can think of its, here of course you can think of the mean and variance. here you can think of in addition to that the correlations, right? So that's what we are going to do. If you, so we define the mean of a, if you have a random variable at x of t, remember if I like this you can also interpret this as x of this is a stochastic process with the time fixed at t. So this is a random variable with the density function f of x comma t. So we can say the mean of x of t is expected value of x of t. Remember, mean is defined as the variable multiplied by the density function, right? But remember this, this stochastic process, this density, this random variable being at a time instant t, this like here, the density function is a function of that particular time instant. You call it t naught, this will be t naught, d what, dx. So this will turn out to be x will go away, but this will turn out to be a function of t. It's possible. So the first observation is the mean of a stochastic process could be a function of time. So the notation must be pretty clear. This x stands for the stochastic process. This is just to show that it could turn out to be a function of a time. Okay. Similarly, of course, if you have a random variable, you can define its variance also. But more important is the what happens. In other words, later we will be interested, if you know the behavior here, what has this to do with the behavior here? So that's dictated by the correlation, right? Correlation of the, so we want to know what is the correlation because if you conclude that this random variable has nothing to do with this, that's uncorrelated. Or it could be completely independent. Most of the cases you hope they have some dependence so that knowing what happened yesterday may give some idea about what is going to happen today. This is the whole basis of prediction and so on, right? I mean, you are certainly not going to predict. We will do some linear prediction also. We already have done, at least we touched upon on an estimation. But the whole idea of predicting something is what is going to happen today is based on what, or at least there is some correlation to the past. So the second order characterization is, the simplest way you can think of is, remember T1 generates a random variable xt1, T2 generates a random variable xt2. So if you have two random variables, how do you, what is the, you certainly know by now, what is a measure for their interaction or dependency? Anyone? No? Yeah, correlation or covariance, right? So we can even start with this function, right? So this is a very important function. The notation generally is Rxx T1 comma T2. Probably will be only talking about this function today. This is not, I mean, what would you call from probability? Expected value of xy is what? No, huh? Well, remember if you have, if you have two random variables x and y, what do you call this one? Anyone? No, I mean you have expected value of xy, then expected value of xy minus mu x. What do you call this one? Yeah, this is covariance. And covariance of x comma y divided by sigma x sigma y is? Right, so this is a correlation. This is absolute value less than 1, right? So we want to develop, if this is 0, we say of course covariance is 0, and we say the random variables are uncorrelated, right? Not independent, uncorrelated, right? And if they happen to be Gaussian, they are also independent. So what I have written is very similar to this. So this is not the, actually this is the correlation. We don't call this correlation, but here the term used is, at least look at this. This is from the same process, this is from the same process. Only difference is at a different time instance. So this is we call this autocorrelation function. The only thing it's a slight misnomer because it's a measure of correlation, but technically we call this to be the correlation. So you may want to divide by their variances, but generally this is taken to be the autocorrelation. It is certainly a function because it's a function of t1 and t2. So if you want to know what this is of course integral x1, x2. Remember you have two random variables. If you have two random variables, this is what we call the joint density function of them. So this is f of x1 comma x2, x1, x2, t1, t2, dx1, dx2. And you can see x1, x2 will, dx1, dx2. So x1, x2 integrates out, you get a function of two variables. So that's a measure of the dependence between two random variables. So one of your jobs in homework is, if I give you if you describe a stochastic process, you want to figure out how to compute that function. Okay. Any questions? So remember, so far I only described two quantities, the mean of the process, mean and autocorrelation function. Mean of a stochastic process and the autocorrelation. So mean is a function of one variable, the autocorrelation is a function of two variables in time. So look, autocorrelation is Rxx t1 comma t2 is expected value of xt1 xt2 star. The star is, if it is possible, some of the processes may be complex, right? So let me pull the star outside. Remember, we are not dealing with any matrix here. So star will come here, xt2, and the whole thing star, right? This star goes inside here, double star is this thing. But look, this can be written as expected value of xt2 multiplied by xt1 star, right? So what is this? Anybody? What is the quantity inside? Alright, so that is Rxx t2 comma t1 star. So this is one property of the autocorrelation function. Rxx t1 t2 is the same as Rxx t2 t1 star. But the most important property is here. So autocorrelation function Rxx t1 comma t2 is defined as expected value of xt1 xt2 star. I just showed it to you that this is the same as Rxx t2 comma t1 star. But let me show you a second property, and then we'll do a couple of examples. Anybody knows the meaning of this statement? We must have discussed this in this class. What is a positive definite function? Anyone? Huh? No, it isn't. So that will be a positive function. See, this is of course a positive function, right? I drew y of t is greater than c, but I have a positive definite. So this is just a positive function, right? So positive definite means autocorrelation has this property. Yeah, say it.
X multiplied by less than multiplied by X transpose.
Right. Except this is the way I have written it, just a function. This is not a matrix, right? You are pretty close. You will see. So pick them arbitrary. You select any T1, T2, etc., Tn. Then it's very hard to imagine, but this is what you have to show. And also you pick up A1, A2, etc., An arbitrary. Okay. They can be complex and arbitrary, but then you form this function. So I form summation I equal to 1 through n. Remember, n is arbitrary, j equal to 1 through n. So this doesn't make any sense, in other words, so far, not yet. But if you can show that this is positive for all values of, for any way you choose, so this is the definition of a positive definite function. Now, it's only a question of your, if you go home, or you can do it here also, you don't have to go home. Anybody knows how to rewrite this in matrix form? Anyone? Hello? You must have seen this, how to rewrite this in using nothing is a matrix here. This is just a function with the two variables, ti comma 2j. This is just a number. This is a number, this is a number. They could be complex. So this whole thing is of course a bunch of numbers added up. As I said, it is not physically very meaningful. But anyone has seen, of course you must have seen quadratic forms, right? You are not kids anymore, right? So what is it? How do you rewrite this?
It's AI, AJ, and in the middle is a matrix.
Oh, even though everything is scalar here, you can rewrite as he says. You must have seen this A1. So let me call this to be a vector A, and then it's if you put its transpose here, well, how do you know this will work? You have to go home and try this. You should, of course. And then in middle, so these are two vectors. This is the transpose of this vector, transpose conjugate. So the question is, what is in the middle? This is R11, R12. Let me call this to be Rij. So R1n. R21, etc., R2n, etc., Rn1, etc., Rnn. So you create a matrix from these scalar values. So what we are saying is that this matrix, so you can write this as A transpose Ra. So this matrix has the property that this is always true. What about A? What kind of vector is A? Huh? A1 through An are arbitrary. So this A is any vector. This is the key. Of course, you don't want to take a zero vector and multiply. So for any A vector which is not identically zero, if you can, remember this is just the definition. This is the definition of a positive definite matrix. So you need to, we say matrix is positive definite if you can take an arbitrary vector, which is what he was trying to say. I didn't want to use X because we already used X as the stochastic process. X transpose the matrix multiplied by the vector. or A transpose matrix multiplied by the same vector. These are any vector, it's transpose. Any vector, it's transpose. Don't take two different vectors, that's not weird. So this is called a quadratic form because it's a, look at here, you can expand it as a quadratic. If you haven't seen quadratic form by now, that means you are watching too much of computer. Stop, high time you look into these things. Because to develop any sophistication, you need some linear algebra at your fingertip. See, this matrix is not, so let me call this matrix to be A. This is, you see, that doesn't mean it won't have, I'll make it even better. It could have complex values as you are saying, but we will see whether this is positive definite or not. So I picked up A to be 4j minus j1. So let me take an arbitrary vector A, A1, A2. So then I should do A transpose AA. So that is A1 star A2, 4j minus j1, A1, A2, right? So this is A1 star, so this is A1 star, A2 star, right? So what is it? 4A1 plus JA2, right? 4A1 plus JA2 minus JA1, right? Plus A2. Now I multiply this row into this column, so I get A1 star multiplied by 4A1 plus JA2 plus A2 star minus JA1 plus A2. So in this case it is simple, it turns out to be 4A1 squared, right? A1 star JA2, A1 star minus JA2, so that cancels, plus what is it? A1 star A2. All right, so let's write it down. So you get plus J A1 star, right? 4A1 square plus J A1 star A2 minus J A1 A2 star plus A2 squared, right? But the middle is what? 4A1 squared. This is A1, A2 star, which is, so A1, A2 star and so this number is the complex conjugate of this, right? So you can write this as plus 2 now you have to show that this is positive. Let me see this. Better way to do this. So if you want to see, write A1 as alpha plus j beta, A2 as gamma plus j delta. Isn't this the same as did I miss a 4 or something? No. Everything is good? Right? So far, is this the same? because 2a1 squared is here, right? This is a2 squared here. Then what are the middle terms? 2a1 star a2. So let me see what this turns out to be. So this is, if we plug it in, this is 4 multiplied by alpha squared plus beta squared. Help me. And so if you don't like this, let's do it here directly. So this is what? Alpha squared plus beta squared, right? And this is plus j multiplied by a1 star is what? Alpha plus j beta. So you just have to do some work. This is how you help yourself. Then gamma plus j delta, right? So everything needs some work. Minus j, a is alpha plus j beta, gamma minus j delta, plus a2 star is gamma squared plus delta squared. I want to show that everything, the whole thing will be positive. So this alpha squared plus beta squared. What about, what cancels out? You can see it yourself.
4 times.
Yeah.
And 4 times alpha squared.
Yeah, 4 times alpha squared plus beta squared. Then what? Then you expand it, a lot of terms are going to cancel, right? So j is common. So you have what? Alpha gamma plus j alpha delta minus j beta gamma minus j squared is plus beta delta. A j I pulled out, so you have alpha gamma, right? Then alpha multiplied by this with a minus sign, minus is here, this minus is coming in, minus minus plus, so plus j alpha delta minus j beta gamma, j squared is minus, minus beta delta, then plus a squared, which is gamma squared plus delta squared. What cancels now? Nothing. Alpha gamma cancels, then everything cancels. Beta delta cancels. Then you have alpha delta twice, beta gamma twice. And j squared comes outside, so we have 4 alpha squared plus beta squared. J squared is minus 1, minus 2 alpha delta, then gamma plus gamma squared plus delta squared. You see beta squared plus gamma squared, so this can be written as 3 alpha squared what is it? Alpha delta. You have, I'm going to take an alpha squared from here, a delta squared from here, then I have this one, right? So I'm going to take a beta and a gamma. Isn't it right? You see, this is alpha squared plus delta squared minus 2 alpha delta, right? So minus 2 alpha delta. The other one is plus here. But you see, this is positive, this is positive, this is positive. End of the day, everything is positive. So I have proved that the whole thing is positive. Right? I just was showing an example. But so this is the property of this matrix. It has nothing to do with this. This matrix is positive definite. I'm going to show that your autocorrelation function has that property. It doesn't matter what, I only showed you that 2 by 2. It could be a 3 by 3 matrix, 4 by n by n, etc. Can be what?
Negative.
Single answer is, what about the diagonal entries?
It's positive.
Hello, a positive matrix, all the diagonal entries are strictly positive. You cannot have zeros here. Off diagonal entries, as you can see, not only they can be negative, they can be complex also. Look at here, right? So a property, if you know, is that, so again, I hope you will use this as a motivation to study. If A is a positive matrix, all these are positive matrices. Here, of course, it is 2 by 2. So that's another, so you should check out books on positive definite matrices. So it's very helpful to stochastic processes and things like that. So I'm saying if these are the properties, if R is a positive definite matrix, you can, this is R, if you call this matrix R2, so this matrix RK, you know what I mean, right? R1 is 1 by 1, this is 2 by 2, 3 by 3, and of course the whole thing is Rn, okay, and so on. These matrices are called principal leading minors, I think. What is a minor of a matrix? You take any number of rows and any number of columns, 2 rows and 2 columns, you get, this is a minor. But if you take the same number of rows and same number of columns, you get the principal minors. These are the leading principal minor, because here you are taking the first row and first column, here you are taking the first 2 rows and first 2 columns, then first 3 rows and first 3 columns. So another property which you need to prove is that if R is positive definite, if and only if R1 is positive definite, R2 is positive definite, etc., or N is positive. So all this, if R is positive definite, all the submatrices are positive definite. That's easy to see. And Rn is positive definite. But what the theorem is, if R is positive definite, if and only if the determinant of R1 is strictly positive, determinant of R2 is strictly positive, etc. There is no point in me telling you all this. You need to prove it. This means it goes both the ways. Of course, it is easy to see that, hello, you see this, if the whole matrix is given to be positive, you can clearly see this is positive definite. How will you prove it? Suppose I take an arbitrary A, but I deliberately put zeros here, and I put A1 through AK, right? Then I use this A and do A transpose RA, you see and let me call this to be B. Then this is the same as B transpose RKB, right? And so if this is positive definite, we know that RK is positive definite. That's easy to show. What is not easy is going this way. So that's why you need to look at the book and proofs, etc. Right? So I'm going to show this very quickly. The proof is, one way it is easy here for an autocorrelation function to show that it is positive definite. Okay. So remember, let me call this mess to be something. Give me a symbol. I'm going to call this omega. Okay. We want to show that this omega is positive, right? I want to show this. I don't know. I want to show that this is. Then I know that this is a positive definite matrix. So the proof is like this. So if I have a stochastic process, consider the random variable y equal to sigma ai x of ti. Look, this is certainly a random variable. Why? Because these are random variables. These are constants. So going back to probability, this is function of multiple random variables. That's a random variable. A random variable will have a mean and variance, whatever, and its own density function. Whatever it is, what will be this value? Expected value of the square of any random variable will be at least what? Huh? Can this be negative? That's my, because this is integral y squared multiplied by the density function of y dy, right? There is nothing negative here. So at least we know. We don't know this, we don't know anything, we don't know how to integrate. You may not even know that, but you certainly know that this is positive, right? So I can conclude that this is positive, right? But let me also use that, so I already know that, so I want this space, so I'm going to put it on the other side. So I know this quantity is positive. Look here. This I know from this expression. But on the other hand, expected value of y squared is, now I am going to plug this in here. That's y multiplied by y star. So that's expected value of y is given to be sigma ai x ti, I equal to 1 through n. Y star is aj x of tj star star, right? That's y star. Because I used two different symbols, now I can take this summation outside. So this now reads I equal to 1 through n, j equal to 1 through n. A's and aj's are constants. So expected value is on the stochastic part. But you see, this is r of ti comma tj. So this whole thing now writes sigma ai aj star rxx ti comma tj. And this is already positive. Look here. You come this way. We already showed this is positive. So the proof is trivial. So we just showed that this is positive definitely. Look here. We wanted to show that this quantity is positive and we showed it. This is exactly the same as there. So the proof is done in one shot for all stochastic processes. So a couple of the homework problems is, I give you a specific problem, ask you to show explicitly that the autocorrelation is a positive definite function. So let's look at some examples. There is one concept that we need to get into at least today, which is the concept of stationarity. But maybe we'll do a couple of examples and then come back to that. Okay. So remember, if you can, we would like to characterize the stochastic process using their density functions. Often it may be difficult, so then we may resort to just a mean. So the best description is, first order description is using the first order density function or distribution function. Second order description is using the second order density functions. But if these things are not available, which is never available, nature doesn't give you density functions, you look at their average behavior in this sense, the mean of the process or the autocorrelation function. So first thing we have studied is autocorrelation also has this non-negative definite property. Okay. This is not a stochastic process, that's just a sinusoidal, right? So generally you may transmit a signal, by the time it comes back, this amplitude, see you transmit a signal, it hits somewhere, the scattering function here, so there will be a return which is what you are seeing. The scattering function here, depending on the surface, may have a reflection coefficient which you may not be able to predict. It may be a surface, but if you look here, the reflection coefficient may be 0.3. But depending on the angle of the ray, if it was here, it may be 0.8 because surface is smooth and so on. That depends on the phenomenon you are studying. Maybe a rough surfaces, right? Or maybe on an aircraft structure, but one place the bending is different from the other place, only few inches away. Or maybe it is a corner. So the wave goes here, it hits here like this. It gets amplified and comes back with a different scattering function. So it's reasonable to assume that in the return waveform, what you are looking, this is also a random variable if you want. But in addition to that, by the time it comes and go back, you don't know the exact delay. So one popular way to model this is that this is a random variable. This is a random variable. But this is a stochastic process now because of this time. So when this random variable takes different realizations, you get a collection of waveforms. So this is a very simple stochastic process. The popular assumption is that this phi is a uniform phase. The density function of phi is uniform. And because the assumption is that phase value could be anywhere from 0 to 2 pi. So you may ask what this is. This depends on the problem at hand. If the reflection is from aircraft carrier or an aircraft, then you have to look at the material and the structure and the possible angles, etc. If the reflection is from a tree, it is completely different, right? If the reflection is from a sandy surface, this is different. So you can assume it has some density function and it has whatever it is, maybe Rayleigh, maybe something else, etc. So generally this is known as the scattering coefficient, right? So what is expected value of A squared? Anybody? What is that expected value of A squared? What is A? You can look at that. A is what? Physically, what is it? What? No, I just told you A is not energy, A is amplitude, right? So what is A squared? Expected value. What? Yeah, average power, right? So for a radar guy like him here, they will call this a mean RCS, mean average. RCS is, what is RCS? Radar cross section, right? So this is the mean return value. RCS stands for radar cross section, but what you said is the right one. So this is a measure of power, but expected value. Of course, you are familiar with this in an earlier course, right? Expectation. So this simply means, or you can read this as a second order moment. So this is absolute value of A squared multiplied by the density function of A. As I said, again, you have to know where the reflection is coming from. And the phase is, you know, the assumption, unless you have reasons to believe that the density function of phase is something else, generally it is assumed to be uniform. Okay. So even in the simple problem I gave you, so the homework is, I just generalize this like this. I equal to 1 through n. I put phi I. So you assume that, also what it says is that you have multiple returns coming back at you, okay? So let's find out the mean and autocorrelation function of this process. So generally that's what it is. So let's do it without the summation, and then you do the same thing at home with the summation. So expected value of x of t is, and I also have to give you that, so you already will see the issue, see. How will I proceed? Anybody? What will I do now? Expected value, huh? Expand what? Oh yeah, but remember I have two random variables here. So I won't be able, so I have to give you another assumption that these two are, it is not independent. And that may not be unreasonable because look, A is because of the RCS value, reflection coefficients. This is due to unknown time delay differences, etc. So we can, if you assume they are independent, then you have expected value of AI multiplied by expected value of cos omega naught t plus phi. And you are saying expand that, right? So here, now if you for some reason you can assume that this expected value is 0, then you don't have to worry about this. But that RCS mean value may not be 0. So let's say that is something mu A. So when you expand the other one, you get of course cos omega naught t cos phi minus sin omega naught t sin phi. So this is mu A multiplied by, remember cos omega naught t is a constant. So expectation is here cos phi minus sin omega naught t expectation of sin phi. So this is going to be what? So this is going to be integral cos phi multiplied by the density function of phi, which is given to you there, right? 0 to 2 pi. So what do you get? Anybody? When you do this, what do you get? Yeah. Because cos phi integral is minus sin phi, right? When you substitute 0 to 2 pi, you get 0. Same thing here. So these two quantities are 0. So irrespective of this, the expected value is 0. So let's go and find the autocorrelation function. Now remember, in our book, we pick it up from chapter 8. You should go through it very carefully. There are lots of examples there. I will not be able to go through all the details in the class. And I said this is opening a floodgate. There are lots of books on stochastic processes. So it's up to you to read up and catch up and so on. I found this book to be very interesting also, Introduction to Random Processes by Balakrishnan. And we'll do some topics little later on, Kalman filtering, etc. from there. So the author's name is, this is B, boy. He's a good guy at UCLA. I think he may be very old now. Right? Old is good, right? At least for... All right, so autocorrelation function is what? Rxx t1 comma t2 equals expected value of xt1, xt2, right? Then substitute for xt1, xt2. xt1 is a cos omega naught t plus phi, and xt2 is a cos omega, so this is t1 omega naught t2 plus phi. So we can write this as expected value of a squared cos omega naught t1 plus phi cos omega naught t2 plus phi. See, something you learned in high school, algebra will be useful. But remember, this random variable is independent of phi. So first of all, you can put like this, right? For the same argument. Then what do you do here? This is where, remember you studied high school cosine and sine. So this is cos A, cos B. Is cos A plus B minus or plus? What is it? Plus, right? Plus cos A minus B. So let me take this to be sigma squared, sigma A squared. Then you have expected value of cos AB is cos A plus B plus cos A minus B, the whole thing divided by 2, I think, right? So that's cos A plus B is what? This plus this. Omega naught T1 plus T2 plus 2 phi plus cos A minus B. A is this, B is this. So you get cos omega naught T1 minus T2. But you see, suddenly there is no, this is just a constant. There is no randomness here. So this goes outside the expected value. So you have two terms, sigma squared by 2 cosine of omega naught T1 minus T2 plus sigma A squared by 2 expected value of cosine of this term. Again we will do what she said, which is we will expand this. So call this to be something plus this. So this is cosine of omega naught T1 plus T2. Anybody knows the answer? What will be the expected value of this? Hello? And just like this, what is the expected value of this? We just showed. Well, you can see here. So this is cos 2 phi minus sine omega naught T1 plus T2 sine 2 phi, right? And the expected value is only on the cosine terms. Expected value of cos 2 phi is what? Anyone? Right, this expected value I am saying it will be coming only on the, only here, right? Expected value here, expected value here. What is the expected value of this? It's the same thing, right? Cosine of 2 phi multiplied by 1 over 2 pi d phi, 0 to 2 pi. This will turn out to be 0. Just do it. So this is gone. Same thing, this is gone. So the answer will turn out to be sigma A squared by 2 cosine of omega naught T1 minus T2. Look at here. There is nothing random about this. This is a deterministic process as it should be. So let me do a couple of examples which are a little harder now, stochastic processes. Especially I want to go to the Poisson process. But before I go to Poisson, let me do a Wiener process. Any questions? Anyway, I think a couple of you who came late, right? So I was saying that few of you have not, remember I had a list here, those who have done in 30s and 40s. Obviously that's not a good grade. If you want, I'll give you the books later. So if you want, I'll give you a makeup exam. But if you come without studying, you'll get the same grades again. So makeup exam will be around April 30th or May 1st, 2nd, etc. My point is go back to the material and do as many problems as possible. Then you come and tell me you need a makeup. There may be 3 or 4 people for, of course anybody is welcome to come. But if you take the makeup, then I'll give you the second. But those who are doing well, there is no, you just concentrate on this material. Right? Remember, there is an exam coming on all this on May 17th. In addition, for those of you who are not doing so well, I'll give you a makeup. And if you want a makeup, you come and you don't have to come to my office today. You just let me know next week, then I'll arrange it probably on a Tuesday, one of those days on May 2nd or something. May 2nd or May 3rd, something like that. All of you should be at this point working on a presentation. If you want to talk to me, that's fine. Because you will be standing here and looking at them and making a presentation. You can't crack jokes, right? And plus there are 10 points. So especially those of you who are not doing well should try to make up on those points. The makeup exam, I'll make it open book for you because I have a feeling I should have made it open book for everybody. But I don't know whether it would have helped. But, so I'm trying my best to get everybody out of this course well, right? But you do have to put in some effort. If I am convinced you are not putting in an effort, then I am not going to move either, right? All right, let's do a few more examples. So what is the point now? Remember, we haven't gone anywhere. I just gave you a definition and we looked at the average behavior. So the question is, if I give you a stochastic process, can you find the autocorrelation of a function, autocorrelation functions? We just did it for a simple function. So let me do for two more examples, then we'll come back to this description of the stochastic process and we will move on. Right? Is this IE or EI? Wiener? Anyone? No. Oh, did I spell it right? Anybody? Let me see.
I would go to the index in the back.
Yeah, but it should be IE. So what did I write? E. Yeah, the same, right? Well, you can pretend to write both the ways, but let's see. Yeah, you are right. I was gambling, right? So you have heard about random walks, right? This is one-dimensional random. A person walks, makes a step S or a step minus S with equal probabilities. So you walk, you take n steps, you will be somewhere here you want to, and let's say this is the step size. And it takes time delta to fix it to. So delta you did S, so then you are here. Then you could go this way or that way with the equal probability. So after n steps, certainly so much time has evolved, right? N steps. You could be anywhere, right? You could be here, or at the most you can only go up n steps, right? So this is the location. I'm going to denote this location as x of t. So you see x of t of course can be written as sigma xi, right? So I guess so xi's are each step. Xi is what is happening here. This is x1. x1, again you can write it down, I'll describe it to you. x1, this is one-dimensional random walk. x1 you can go in the plus side with a step size is s. So you go s this way or you go backward. So then with the equal probability, it doesn't have to be equal probability, let's say equal probability. Then x2 is the next one. So if I add x1 plus x2, you will get the location at the end of 2 steps. So that will be the location at the end of n steps. And of course I am going to define it this limit. I am going to make very small number of steps so that the step size is small and the delta is also small. In other words, the time it takes to execute a step is small. This is what happening in this room with all these gas molecules, right? It's randomly hitting each other and going around. That's the Brownian motion. That's 3-dimensional random walk. If you do this on 2 dimension, that will be a 2D random walk. So right now we will just do the 1D description. Later in the book there is a chapter devoted to all this. So generally I do that when we do queuing theory, but I think this is good enough to start with. So remember, probability of xi equal to plus s, I am going to assume it to be half. Probability of xi equal to any step minus s is also half. Right. So expected value of xi is what? Anybody? Xi takes 2 values. One plus s with probability half and minus s with probability half. So expected value of xi is 0. So what is the variance or what is the expected value of xi squared? Anybody? Before I compute? 0?
No.
What is it? Right, s squared over 2 plus s squared over 2, right? S squared multiplied by half plus minus s squared multiplied by half, so s squared, right? And it is reasonable to assume, hello, that all this, of course, like a drunken man, what happens now is all these steps are independent, right? So we'll also make the assumption that the previous step has nothing to do with this step. So what about expected value of x of t? Anybody? What is so the limiting process of this thing is called a Wiener process. So you understand a Wiener process description. So we start with discrete, make the step size small, you do it fast, so wherever the random, so that's what is happening with all the gas molecules, right? So that's a 3-dimensional random walk, completely different from here. So you can imagine in any number of dimensional space a random walk also. And so the behavior in 3 onwards is different from 1 and 2. That's for another day. And so what is the expected value of x of t? Look here, if you have studied random variable, expected value is sum of the expected values of each of them. 0, right? So that's good. So that's not Poisson process, that's still Wiener process. And the expected value of x squared t is what? So x squared t is, look here, expect a square is square here. So you can certainly see it is expected value of, many ways you can do it, so certainly this is true. This can be written as double summation expected value of xi xj, right? ij. But when I is not equal to j, what happens? Remember, we already described that what happened. Oh, they are independent, that's by assumption. And each of them are 0 mean. See, I'm using all probability. So what happens when I is not equal to j? 0. And so this only matters when I equal to j, right? So this is summation expected value of xi squared, I equal to 1 through n. And so that each of this is what?
S squared.
So this is ns squared, right? Right? But we look at here. N is, we assume that we define the n using the how long it takes for each step to execute. So n is t over delta, right? Multiplied by s squared. So Hello, I hope you, right, when I is not equal to j, expected value of xi, xj is expected value of xi multiplied by xj, and that is 0. And this, of course, I can write this as t multiplied by, or s squared over delta multiplied by t. Okay. So my key assumption in random process, look at here, s is what? What is s?
Step size.
And delta? Both are small, isn't it? But I'm going to make the assumption that the step size goes to 0 and the delta goes to 0. To define the Wiener process properly, I'm going to assume that the time it takes for each step is getting smaller and smaller, and the step size itself is, but I'm going to assume that they go, so s goes to 0 and delta goes to 0, but such that s squared over delta is a constant. That's the assumption. So this is of the form alpha t. So a Wiener process, this is also the variance of the process because the mean is 0, right? So of course what we are interested is what is the, so process being defined, I want to find out what is this quantity for a Wiener process. So you see, let me look at, let me take T2 greater than T1. So let me consider this quantity. Look here, what am I have the time axis, this is t, this is 0, this is 2. So the Wiener process is going on here, right? I mean, imagine the steps are in that direction. That's the Wiener process, x of t. This way, you move plus s or minus s, right? But everything is tiny and time is in this direction. So what is this? xt2 is what? From here to here, right? Minus xt1 means up to here. So this is xt2 minus xt1, right? Right? So whatever is happening here, so let me expand this. So this of course can be written as expected value of xt2 multiplied by xt1 minus expected value of xt1 squared, right? And what is this value? Hello? What is this value? Huh? Alpha t1, right? We just found out here, right here. Expected value of x squared is alpha t1. Now, what is this value? So this is what you are looking for. This is rxx t1 comma t2 minus alpha t1. We got the answer, right? But look at here. Let me use another argument. What is happening here? This is what? This is the random variable. Some of the random variables here, right? So if you want, I can write this as sigma xi, but I goes from n plus 1 through somewhere m, right? This is sigma xi or xj. J goes from 1 through just up to n. This is starting from n. So what happened? These random variables and these random variables are independent. Each of them have, so this is equal to 0. So this is equal to 0 and you can solve for rxx t1 comma t2. So what is rxx t1 comma t2? Look here, we did this argument when t2 is greater than t1. What do you get? Alpha t1. So what happens if t1 is greater than t2? This will be the other way. What will be the answer? When t2 is, or when t1 is smaller than t2, this is alpha t1. When t2 is smaller than t1, this will be alpha t2. You just go through the same argument. You just flip the two variables. So of course, together you can write this as alpha multiplied by a minimum of t1 comma t2. Okay. Now I'm going to give you a challenging problem. You may not be up to it, but I'll give you the problem anyway. So you see, if you use this argument, hello, listen to me, we showed an important thing. A minimum is is a nonlinear function of two variables. We just showed. So what kind of function is this one? From our argument. It must satisfy all this, right? Because I just showed you that it's an autocorrelation function. Every autocorrelation function is a non-negative definite function. So you should be able to go home and start with this function and show that if I generate a matrix using that, you should be able to show that it's a positive definite function. See whether you can do it. That's one of the homeworks, actually. So as I said, it takes some doing. If you don't do it, I'll of course show you the solution next week. I think there is also a problem at the back, which is precisely this problem. Right? So everything is about autocorrelations. Again, as I said, it's up to you how far you want to go doing problems. Right? But that's a decent problem, number 5. Of course, the easiest way is you use this argument. You say this. But suppose you didn't know this. I just give you this function, minimum of T1 comma T2. From here you generate this matrix. Hello? Steve? You take the minimum and create a matrix. Then you want to show that that matrix is a positive definite property. That's what the problem number 5 is asking. It must be true because one way we are able to argue that this is an autocorrelation function. Okay. So minimum is an autocorrelation function. So how do you create a matrix 2 by 2 which is minimum? So look at here, this is 2 by 2. So what will be the entry here? So if it is n by n, T1, T2, Tn. So what will be the first column? Anybody? I have minimum of T1 comma T2. So take some numbers this way. You can take arbitrary TAs. You can certainly you can rearrange them, right? So T1 is the smallest, Tn is the largest. Let's just do for 2 by 2. I have two numbers. So what will be the entry here? Huh? Minimum of T1 comma? T1, which is what? T1. And here? 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 T1? Oh, very good. And this of course is easy to see that this is positive definite. Look here, this is positive definite. The 2 is, what is the determinant of T1, T2 minus T1 squared. So that is, T1 is common, T1 multiplied by T2 minus T1. T2 is greater than T1, so this is positive. But I want you to do for n by n. You cannot sit there and do this. So see what you can do, right? So is there another way can you do it? Okay, so now let me go to Poisson processes, very important problem. Or maybe before that, so a Wiener process will look like this, right? See step size. A small step size, right? So this is the way Wiener process is going to look like. Now, so that's x of t, and y of t is what? Minus, so if x of t is plus, it's going to be, what did you say?
Depends if it's even or odd.
Right. Yeah. Remember, right. The x of t is going so x of t is going to be even or odd because it is n delta, right? So depending on that, this is only going to take two levels, right? So this is the same as saying that. So it's a two-level function. So let me just. All right, so maybe before I come to this, let me do the Poisson process, and then we can come to this, because there may be a bit premature. Also, things are arriving at random. So once again on time axis, and next arrival could be anywhere. So if I take some interval, if I take some interval and say there are n arrivals, it's reasonable to assume that if I wait longer and longer, there will be more arrivals, right? So the n is the total number of arrivals. Is proportional to the duration that you are looking for, okay? That's a reasonable assumption. And now I take some small interval within this, some delta. And the number of arrivals here are k. That's what k is. Okay. So k is the number of arrivals in delta. So what will be a common sense value for this? I take some sub-interval in t. What is the chance that an arrival that's going to happen in the t will fall inside there?
Times
No n. I'm saying I have two intervals, delta and t. Yeah, so this is reasonable to assume it is delta over t, right? This is saying that what is the probability that any one arrival will be in, if you want to put the word any one arrival in delta is proportional to delta over t, because the arrival is certainly going to be in t. So what is the probability of k arrivals in delta? Then it is going to be like a Bernoulli process, right? So probability of one head happening is p. We are asking what is the probability of k heads in n tosses, right? So that's n choose k, p to the power k, q to the power n minus k. So you have to write here, this is given there are n arrivals in T. So this, of course, if you write this is n factorial over k factorial, n minus k factorial, right? Multiplied by p to the power k, q to the power n minus k. So this you can write it as n into n minus 1, n minus 2, etc., n minus k plus 1, right, over k factorial. I just get rid of this. Multiplied by p. P is what? Delta over n, delta over t to the power k, 1 minus delta over t to the power n minus k. So let me do some simplification here. I'm going to, so that much is true, right? That's just the, from coin tossing, right? Let me multiply by n to the power k here. So I just need to put an n here, right? Because this nk cancels. And I'm going to take this into, this is done in the book. I'm going to take this inside each one n. So this is 1. Look here. I'm going to put one n divide here, another n divide here, another n divide here, etc. So this will be 1 multiplied by 1 minus 1 over n, right, multiplied by 1 minus 2 over n, etc., 1 minus k minus 1 over n. Then n delta over t n itself is what? Somewhere. Yeah, so n is proportional to t. So I'm going to assume n is of the form some mu t. Right? So instead of n, I'm going to substitute mu t, delta over t to the power k, 1 minus so this is also the same as, what is it? Right, mu delta over n by n. Right? Oh, so here t cancels. And let me call mu delta, not mu delta. Right, so mu delta, so look at this. This can be, now you push n to, let's take the case where limit, you can write another line if you want, this is, yeah. N go to infinity. You see this is 1, n goes to infinity, 1 minus 0. So there are, look here, there is only, you can count the number of terms, 1, 2, 3, there are only k terms. So in a finite k places, you make n goes to 0, this whole thing becomes 1, right? Now this is a standard expression. This is what happened. There is also a k factorial somewhere, right? This k factorial. So that stays here. This is simply t goes away. So that is mu delta to the power k over k factorial, right? And let's look at this. Here, you push n to infinity. Again, a finite number of terms. So n goes to 0, 1 to the power k, so that's gone. That's 1. Except this. Anyone remembers this? 1 over 1 minus x to the power n, limit n tending to infinity. Look, without this, of course, it is 0. Huh? So if you raise this to the power n, anybody? So this is e raised to? Minus x. No, because this is minus. So how do you know this is? You expand it as a binomial expansion and then you will get the two terms be the same. So here you get e raised to minus mu delta. So what is it? Look at here. So what we have shown is if you have random arrivals and if these arrivals are if you consider over a very large time, a very large interval, these arrivals are independent, then the number of arrivals in any duration, so if you take some duration t, the number of arrivals appearing here is Poisson, because this is going to play the role of delta now, right? Delta is I replaced it. If I take some interval t from somewhere, so delta is going to be played by the role of t. So then what is this distribution? Anybody? Poisson, right? So now if I replace delta by t, I get, that will give you this will be the probability of k arrivals in t. So I'm going to define a Poisson process x of t as the number of arrivals in 0 to t. So x of t is the number of arrivals in 0 to t, and I will also denote it, n is for the number. I can use this notation. So what it says is we just derived it. If so this t is pushed to infinity. So if I look at over a long time, then I go through this argument, the number of arrivals in any finite segment t is given by this, but this is Poisson, except it is not a Poisson random variable. The density function also has t now. Hello, right? So let me get rid of all this and I'll just define a Poisson process. This was sort of a motivation. This generally I do in probability class, the first piece. You define Poisson process using, you can start like this. So now it's no more a mystery. I'm just writing what we just derived. So we say x of t is a Poisson process with parameter some lambda mu t. If the number of arrivals is given by e raised to minus mu t, mu t to the power k over k factorial, right? And k could be any number, 0, 1, 2, 3, etc. K of course is less than or equal to n, but n is pushed to be infinity. So it goes all the way to this. And the second is the random nature, the number of arrivals here. If you take some interval here, what is happening here, it doesn't influence here. So what it is saying that the number of arrivals in then the arrivals in those intervals are independent. this is a long topic. I'll do a little bit now, some of it now. Then I do want to cover one more item. Maybe you'll see, or we. So what this basically says is here, if you take time instant and if you mark T1 here, T2 here, and T3 here, T4 here, or you take another case and you mark T1 here, T3 here, T4 here, but you mark T2 here, then you see the number of things happening here and here are independent. That makes sense because arrivals here has nothing to do with the arrivals here. But this interval, number of things happening here and number of things happening here are now messed up. They are dependent. So these are independent. This random variable and this random variable are independent, whereas this random variable and this random variable are dependent, right? Now there is a this thing is made a bit more rigorous if you go through my lectures number 15 or justice on Poisson processes. So anyway, you can start with this as the definition of Poisson processes. I just showed you why this is physical, right? So it starts from arrivals being arbitrary and not influencing the previous arrivals or the next arrivals. So a data packet that is coming over the network, if it has this property, it is Poisson. But if the data packet is influenced by what is happening here and there, then the Poisson assumption is not true. So we will study now the Poisson stuff. So the immediate thing is to find out the mean and autocorrelation function of a Poisson process. Then I will do, since we have closing to the end of the class, I'll keep talking about Poisson as much as we can. And the next key concept we'll start next week, which is the concept of stationary processes. So remember, if you construct an autocorrelation function, then you should be able to show that its autocorrelation also is non-negative definite. So you can study -1 to the x of t, but when x of t is a Wiener process, but I just got a bit confused. -1 to Poisson process is the telegraph signal. We will see. Okay. But let me deal with the this thing first. So these are, remember in queuing theory, this is very important. This point is known as the first arrival. This is the second arrival. This is the third arrival times. These arrival times are random. So of course we want to know what their so we need to expect the mean of the stochastic process x of t and the autocorrelation function for a Poisson process. So what is mean of the x of t? Look here, mean is what? X of t is what? What do you mean by Poisson process? If you fix time, look at here. If you fix time, this random variable behaves exactly like Poisson with this parameter. So what is the mean of this random variable? Anybody? Mu t, because the mean of a random variable is just the parameter. The parameter here is mu t. So if the probability is good, then you know the answer immediately is simply mu t. Here, so here this is mu t, and autocorrelation is we have to compute to this quantity. So again, we will try to use the, so I take T1 here, I take T2 here. So I take the case first when T1 is less than T2. Then we will do for T1 greater than T2. But if I get one case, you will see the answer, right? So I know that whatever is, this is x of T1, right? But that's also the same as number of arrivals from 0 to T1. And this is x of T2. So is x of T1 and x of T2 are dependent or independent? Dependent because, right? But you see, if I consider this one, which is n of T1 comma T2, this and this are independent, right? Right? But n of T1 comma T2 is the same as, from the picture you can see, x of T2 minus x of T1 if you define this properly, right? And I know that these random variables are independent, right? Right? Independent. So expected value of this is what? 0? What is the expected value? Independent means this is expected value of 0 T1 multiplied by expected value of n T1 comma T2. But this is the same as expected value of xt2 minus xt1, right? So what is the expected value of this? Anybody? This is the same as xt1. Mu T1, and this is?
Mu T2 minus.
Right? So this is mu squared T1 multiplied by T2 minus T1, right? But I can also write this as, look at here, I can also write this as expected value of x of T1 multiplied by xt2 minus xt1, right? Right? Because this is this, this is this. So the same thing, let me expand this on this side. So here I get expected value of xt1, xt2 minus expected value of x squared T1. For a Poisson random variable, remember x of t is Poisson, so its mean is xt1. What is its variance? I'm sorry, x of t is T1 is Poisson, so the mean is mu T1. What about variance? Mu T1. So what is the square of the Poisson random variable? Hmm? Right? But now look here, this is equal to this quantity. So let me equate this. So that's mu squared T1, T2 minus so this is with the minus sign here. So this is, the first term is here Rxx T1 comma T2, right? Equal to this one minus mu squared T1 squared, right? So when I bring this to this side, this is plus mu squared T1 squared goes away. So from here, this is equal to this, right? Hello? What is your problem?
No.
No means yes or no?
I mean, there is mu T1 in the left, on the left, and that also on the right.
All right, so this is equal to this here, mu squared T1 T2 minus mu squared T1 squared. You see, this term cancels with this, right? And you bring this term to the other side. So you get the answer to be what? Mu T1, mu squared T1 T2 plus mu T1, right? Right? Look at here, mu squared T1 T2 plus mu T1. This is when T1 is less than T2. What happens when T1 is greater than T2? So that's mu squared T1 T2 plus mu T2. Again the same thing. This is, so you can together if you want you can write this as mu squared T1 T2 plus mu minimum of T1 comma T2. Okay. So this is the autocorrelation function of a Poisson process. Again, highly nonlinear. So I'm going to go into a Poisson process a bit now, and this is very important in queuing theory, so it's good to do a little bit. No, but before that, if I define, this is what I made a mistake. So if x of t is Poisson process, I can define, of course with the Wiener process also you can define and you can try to find the mean and process, but this is what is known as the telegraph signal, because it makes sense. This only takes integer values. So a Poisson process will look like this, right? If this is time, see the signal is 0, look at here, signal is 0 at time tau on one arrival, then wait at time tau 2 second arrival, so it goes up. So a Poisson process is going to look like this, right? The jump is when an arrival comes, right? So if I take and generate, so this is my x of t. So you can see if you define okay, so here, whereas here minus 1 to the power 0 is 1, so it always starts here. Then here it will change the sign, here it will change back, change. Things like this, right? You don't know when this is going to change. That's why it looks like a telegraph signal, because it's either plus 1 or minus 1. So so I'm going to leave this to you. This is done in the book. Find the mean and variance. Mean and autocorrelation function. Mean is easy because expect y of t only takes, so this is the same as when probability of x of t is even minus 1 multiplied by probability of x of t equal to odd. X of t equal to even means what? That is the same as probability that x of t equal to 2k, right? And k goes from 0 through infinity. So this is minus summation of probability of x of t is of the form 2k plus 1, right? And k goes from 1 through 0 through infinity also. So this is of course e raised to minus mu t to the power 2k over 2k factorial. And this whole thing, summation is k equal to 0 through infinity. This is the odd terms of a exponential, so that's cos hyperbolic mu t. So this is minus e raised to minus mu t, summation, same thing, mu t to the power odd terms, 2k plus 1 over 2k plus 1 factorial. So this is sine hyperbolic, right? K equal to 0 through infinity. Odd terms. So together, if you write it down, e raised to minus mu t, cos hyperbolic minus hyperbolic is e raised to minus 2 mu t. That's the mean. Let me leave it to you to do the autocorrelation function. So it goes like this. I'll just do one term. RYY T1 comma T2 is what? Probability of, not probability, expected value, right? Expected value of YT1, YT2, right? So you just need to go home and do some stuff. But YT1 takes two values, plus 1, minus 1. YT2 takes plus values, plus 1, minus 1. So there are 4 combinations, right? For example, the first term will look like 1 multiplied by 1, probability of yt1 equal to plus 1, and yt2 equal to plus 1, right? Right? Plus the second term, so there are the 4 terms. Let me show you how to do one of the terms. Remember what I was saying is if you expand e raised to x minus x, you have 1 plus x you have 1 minus x plus x squared by 2 factorial minus x cubed by 3, etc., right? So if you collect this as like this, plus terms and minus terms, 1 plus x squared by 2 factorial plus x4 by 4 factorial. And this is x plus x cubed by 3 factorial, etc. So this is known as cos hyperbolic x. This is known as sine hyperbolic x. So you have another formula. E raised to minus x is cos hyperbolic x minus sine hyperbolic. You seem to be bored? All right, so let me show you how to do one term. So this is, of course, this term is the same as probability of x of t1 equal to e1 and x of t2 equal to e1. Unfortunately, these two are not independent, right? Look at the t1 and t2 are overlapping. But if I call this to be a and this to be b, this is probability of A intersection B, which is the same as probability of B intersection A. AB is the same as BA, which of course you can write it as probability of B given A multiplied by PA if you want. Why am I doing all this? Because this now reads probability of xt2 equal to E1 given xt1 equal to E1 multiplied by probability of xt1 equal to E1. So what? So read this now. So x1 and x2, remember, is here, right? t1 is here, t2 is here. What is the probability that, look, the number of xt2 is this, all the arrivals in up to here. What is the probability that all the arrivals from here to here is even, given that the arrivals from here to here are even? What can you say? That's the same as saying what? Listen to me, this is xt1, this is xt2, this is n of t1 comma t2. So saying that, look at here, saying that this is even, given that this is even, then this has to be what? It has to be even. This cannot be odd, because if this is odd and this is even, this will be odd. So if this will be even, given that this is also even, is the same as saying that this is even, right? So this is the same as saying the number of arrivals in t1 to t2 is even multiplied by x of t1 is even. Remember, we did this earlier. This is e raised to minus mu t1 cos hyperbolic t1. So using the same, remember, this is a Poisson with parameter mu multiplied by t2 minus t1, right? So this is e raised to minus mu t2 minus t1 cos hyperbolic mu t2 minus t1. So you just have to do all the 4 terms and put it together. There is some work to do. So even stochastic processes looks like nothing is easy, especially if you want to do stuff. We have a little bit of time, so I'm going to go more into Poisson processes. Okay. Or maybe let me take a few minutes to describe the stationarity which you need in the problem. Any questions here? Why this is known as semi-random? Remember, I told you a telegraph signal you can understand why this is called telegraph because this looks like this, right? At 2 level. Why it is semi-random is what is the value at t equal to 0 always? 1. So it looks like there is no randomness here. So you can get over that problem by randomizing this by a. So take a to be a random variable, probability of a equal to +1 is half. Probability of a equal to -1 is also half. So if you multiply by a, then you don't know which value will start. So if you multiply by a, then this y is known as the random telegraph signal. Okay. So it's a trivial stuff. So you multiply by a random variable which is independent of this. This random variable is a Bernoulli random variable. Like you toss a coin and decide. If it is head, you put +1. If it is tail, you put -1. So it will not be always starting. It may start here or here, but you don't know which one. Right? If you are willing to do that, then you can cut the semi. It will be just a random telegraph signal, but the rest of all this will stay the same. Any questions? I'm just thinking when to, I know you are tired, so maybe we'll just continue with this example rather than, so you can do all the problems, I guess as I have asked a question in 2, is YFT WSS, just remove that, you don't need to answer. Problem 2, this second last line, just cut it off, right? So why don't you reword the problem? But you have to write something there. You need something to do. So the question is, find RYY T1 comma T2. Find in number 2. Find the autocorrelation function. What WSS is, we will discuss next week. But let me do a little more on Poisson because some of the homeworks are related with that. So remember, arrivals are random. So if the arrival is random, then it has a density function. So you can ask, what is the density function of the first arrival? What is the density function of the second arrival, etc. Right? That's the definition of the distribution function of tau. By notation, you know what is tau 1, right? Tau 1 is the first arrival. I noticed it. This is the first arrival, second arrival, etc. So you can also take this as the, even though it's going to take time, arrival of your children, right? First arrival, second arrival, etc. So this is the same as saying that what can you say about this number? saying that the first arrival is less than t is the same as saying that the number of arrivals, remember 0 is here, tau is somewhere here, saying that the number of arrivals in 0 to t is what? Hello, you need to think here. You need to stop, make the brain work. Well, you have to be careful. Is this or what is it? Saying that it is, you see, you are saying, I know for sure the first arrival is, let me put it this way. Then, first arrival is less than time tau. That means the number of arrivals in 0 to t is greater than 0, right? This is the same as, but this is the same as saying 1 minus probability of number of arrivals in 0 to t is it has to be equal to 0 because look, the number of arrivals can be 0, 1, 2, 3, etc. So if this is already strictly greater than 0, then this is equal to 0. What for if remember this is same as saying probability of x of tau equal to 0. What is the x of tau is Poisson, so what is the probability of that equal to 0? Anybody? We had it somewhere here, right? Probability that the number of arrivals in x of t equal to k is e raised to minus mu or lambda t to the power k over k factor. So what is the probability that x of t is 0? X of tau. E raised to minus mu tau, right? So look at here, that's the distribution function of tau 1. I use the variable different from the random variable, okay? This is the random variable that we are talking about. This is just the running variable, okay? So what is the density function? F tau 1 is, what do you do from the distribution function to get the density function? So that's d by d tau of f tau 1 tau. So that comes out to be what? Mu e raised to minus mu tau. Of course tau is positive. So what is the density, what is the decision? So this is an interesting result, it's exponential, right? So the arrival time, the first arrival time is exponential. But look here, once the first arrival happens, the process has, as I said, whatever is going to happen later is independent. So if I mark it right, so let me remark it. I am going to, this is what I am going to call the, this interval, let me use another notation. So this is the interval from 1 to 2. So from here things are starting all over. This is from here it is like another first arrival. So what will be the distribution of this? Anybody? Delta 1, 2. Yeah, you are correct, but you have to argue it correctly. So it's all done correctly here. 0 to tau 1. So this is according to my notation delta 0, 1. This is exponential. Once something happens, things are all over. It's back to square one. So the second arrival is as good as the same as the first arrival happening beyond this. So this is exponential. This is exponential. So if you are convinced, then you can write another statement. The inter-arrival times all are what? Inter-arrival time means the time between two arrivals. What is the distribution of that random variable? We just derived. Because this interval time is the same as this. So each are exponential and they are all. So that's the key result, right? Inter-arrival times, you can write it down, are exponentials and independent. So let me not complicate it. I am going to simply call them delta I. So delta is from I minus 1 to, let's say, I. So tau j is what? Tau j is sigma delta I equal to, let's say, 1 through j. So these are all what? These deltas, so this is like delta 1, first arrival, the time to the second arrival, etc. up to the ith one. I mean jth one. Each of this is exponential. All of them are independent. If you add a bunch of exponential random variables with parameter mu, what do you get? Huh? Exponential plus exponential. I should degrade your grade. Huh? Exponential plus exponential.
No, it's
Gamma,
gamma.
right? So each of them is exponential. If you add n independent exponentials, you get gamma with parameter n comma lambda, n comma mu here. So you also conclude that this is gamma. What is gamma? What is tau j? Anybody? In physical words, what is tau j? Look at the picture. Jth arrival. First arrival, second arrival, jth arrival, right? Gamma with the j comma mu. Okay. Exponential is a special case of gamma, 1 comma mu, right? So it's done a bit more rigorously in the notes, so you should look at the proof. And these are all very classic results. Any questions? Yeah, I mean, as I said, my lecture number 15 is just on Poisson processes. And this is also re-derived there couple of different ways.
The I is 1 to gamma, right? So it's delta 1 plus delta 2 plus 2 delta gamma.
I mean, see, I'm saying, just say this is delta 1, this is tau 1, and you add another delta 2, you get tau 2. So tau 2 is already delta 1 plus delta 2. Tau 3 is here, this is your delta 3. So delta 3, the way I am describing, is the time between the previous arrival and next arrival. 3 means with the time between 2 and 3, right? So if tau j is here, you end up with this notation, this is delta j, right?
Yeah, but I mean, I is 1 to gamma, so...
I is 1 to gamma, I is 1 to j.
Oh, that is j.
Yeah. Let's say j, right? Look at here, this is 1, 2. So tau j is delta 1 plus delta 2, etc. You don't like tau j, let's write tau n, so there is no confusion. Tau n is up to what? Huh? Delta what? Look at here, which arrival? So this will be delta n. Each of them is exponential. Each of them is exponential with parameter mu, and you are adding n such independent, right? These are independent. So what do you get? Gamma n comma mu. Okay? Again, a classic result in, so let me do one more, then we will quit. Then we won't quit, then I want to show you another result. This is what happens in a bus station, right? And airports, people come in. If you stand somewhere, you see people coming one after the other. People are getting out of the flights and going out, right? The same thing in Port Authority, right? You stand at any one gate, people come in, people go, right? So I'm going to assume that the arrivals are Poisson with parameter mu, and the departures are also Poisson with the parameter lambda. Either way, maybe lambda, let me reword it. It doesn't matter. I think this is what, again, a classic result. You understand this, right? One is arrival processes, other one is departure. You go to a taxi stand, and you see that people are coming and queuing up for taxi. Taxis are coming, people get into the taxi and go, right? So again, the same situation. So what do you call this interval? Anybody? What do you call this?
Waiting time.
Or, no, remember, this is one arrival, this is another arrival. So, inter-arrival, right? And what is this one? Inter-departure, right? So this is the arrival between, so let me use two different notations. Look here. So tau is the inter-arrival. So what we want to know, let me define z of t. Let me define a new random variable z. Z is the number of departures in any inter-arrival type. You understand what I'm trying to say? Between, see, look here, in this case, between two arrivals, there are three departures. If you look here, between two arrivals, you have two departures. So it seems to be a random variable, right? You could you could go home and do the other way also. Between two departures, see how many arrivals are there. That will be another random variable W you could study. So definitely this is a discrete random variable, right? So I want to find out probability of z equal to k. Isn't that true? So of course the look at here. Why is it difficult? I am not look at here. I am not picking a fixed duration and asking you how many. The duration itself is random. This is randomness over randomness. This is random. This is random. So if this was a fixed, of course this is easy to say because the departures are a Poisson process, right? Probably. So let me call this process to be x of t. This is y of t. So probability of, if you take any interval, probability of y of t equal to k is, of course, e raised to minus, in this case, mu t to the power k over k factorial. But that's not what we are asking. We just don't know this itself is random. So the way I'm going to do is I'm going to condition it on tau, then we will get rid of the randomness, right? So you understand this formula, right? For any random variable, of course I can I can bring in another random variable x equal to small x, then I can I can get rid of that, right? So you do, how do you get rid of it? You get the joint density function and integrate this out. Remember, density function of x is joint density function of x and y integrated out. This is the same as probability of z equal to k, x equal to, given x equal to x, multiplied by fxx dx, especially if this is continuous. Okay. So that's the formula I'm going to use here. Integral this z equal to k given tau equal to x multiplied by f tau dx. I could have used here t. If you are comfortable, we'll use t here. So tau is what? Tau is this. So I want to say that this duration is t. I fix a t, right? You know this formula. One random variable, you can take the joint density function and integrate out to the second one. Or you write this as conditional and integrate out to the x. So here integration is on t. T is this interval. Interval could go from 0 to infinity. Look at this. This is given to be what? What is, this is the inter-arrival time for the arrival. So what is its distribution?
Exponential.
We just learned. What is it? Exponential with?
Lambda.
So this is lambda e raised to minus lambda t dt. Okay. But look at here. This is interesting thing. If this t is fixed as small t, then you know how many departures are here. How many departures are here? That's exactly this formula, right? If this t is fixed as t, then it is this. So that's going, this formula is going to be e raised to minus mu t to the power k over k factorial. So this only lambda goes outside now, integral 0 to t. I guess mu also goes outside. I have mu to the power k lambda. Then you have, what do you have? T to the power k over k factorial e raised to minus lambda plus mu dt. So let me call lambda plus mu t to be x. So t is x over lambda plus mu. So this integral now becomes lambda mu to the power k integral. So t is x over lambda plus mu. So when, look here, when t is 0, x is 0. When t is infinity, x is infinity. T is x over lambda plus mu to the power k e raised to minus x. Dx is, dt is dx over lambda plus mu. So I pull out all the constants. So I can write this as lambda over lambda plus mu. I missed a k factorial somewhere, right? There is also a k factorial here. So I have a, then I have mu over mu to the power k over lambda plus mu to the power k. So that, then you have k factorial. Then you have integral 0 to infinity x to the power k e raised to minus x dx. Anybody knows the answer to this? Gamma k plus 1 or k factorial actually. So this is k factorial. So this cancels. What do you get? You get it of the form, this form. Because if you call this to be p, this is q. Look at this. And what is this distribution? So you have seen it, right? So here is, if you were dying to find out a physical reason for geometric, here is an explanation. The explanation is if you have two queues, people coming in and going out of the bank, and if you want to know what happens, because bankers may want to know this is, right? This is between two arrivals, how many people are getting out, or the other way, between two departures, how many people are getting in. So what is shown is that that's a geometric distribution. Well, what is the question?
Why PZ equal to given T equal T is a distribution function.
Here? Here? Why this is? After all this, look at here. It is given to it here. It is given to you that that's also a Poisson function. Don't shake your head so quickly. What is the question? Let me understand. What are you saying? No, I'm saying if you fix the inter-arrival time to be t, then you know that if this is t, the number of departures are given by this formula. So tell me again, what is your question? No question? Then why did you ask a question? Huh? Question is what?
Why the distribution function is
You mean here or here? Here? No, ask him what he's
Trying to ask why PZ equal to K given tau equal to Z
This-
without Poisson distribution.
Yeah, that's because this is the same as a probability of y of because if this interval is say whatever here, no, so this has to be written as, that's the same as probability of right? Because say, what is C? C, remember, C is the number of departures in any interval. So I am taking a typical interval tau k and tau k plus 1. We know the duration between these two is an exponential random variable. I am calling that tau. Let me fix that tau to be t. So if I fix that tau to be t, then the number of departures are precisely this. So the number of departures in somewhere to somewhere plus tau is precisely given by this formula. That's the definition of the Poisson process. And so if I define this to be P, you can see this is Q. So it turns out to be, so the interesting result is this is geometric. So this is geometric with the parameter P equal to lambda over lambda plus mu. Lambda corresponds to one Q property, mu corresponds to the other Q property. So if arrivals are slower than the departures, the P will be less than half, right? And so on. If this is mu is 2 times lambda, then this is 1/3 and so on, or the other way. So we can go on from here. I guess I just asked the same problem in one of the homeworks, so you just have to repeat the thing. And then where this takes us to is next is the coupon collecting problem. In other words, anybody knows what the coupon collecting problem is? Let's say you have our baseball card collection, right? So you have n types of baseball cards. And somebody sells one card, I have one card. Now I want to get the whole series, right? So the easiest way is, let's say in the serial boxes, sometimes they put some sort of card. Let's say the baseball, nobody puts a baseball card, but let's say a cereal box, you open it, you can eat the cereal, but on top of that you also get a card. That card has some number, okay? Then you buy another cereal box, you get another card. Unfortunately, this card number may be the same as this. Then you are not getting a series. So the question is, how many boxes should I buy to get, suppose there are n different cards and you want to get all the cards so that you have the whole series. Question is, so at least it is clear that you have to buy n boxes, right? But you can, if you buy randomly n boxes, you may not get all the cards. You may have to keep buying and eating more and more cereal, right? So the question is, on the average, how many boxes do you have to buy to make the whole thing? So this is also comes up in disease, because say for a disease to catch, maybe 10 things you have to do poorly at the same time, right? So you do one, you get away with it. Next time you may do it again and maybe you get 2 of them into it. So you keep doing it. So the question is, how many, so you remember there is a statement, right? You keep doing it, you will end up in trouble, right? So the question is, how long would it take to catch up with the whole? So that has interesting applications. We may get back to it. Let me review something. Let's finish what we need to do before we, so we'll continue with this next week. I do want to quickly point out something he has done in his exam, which motivated me to think, and I want to show you some simple formulas to find the moments of Poisson random variables. And remember, you needed binomial random variable 4th moment, and you all struggle. So this is the question. X is binomial with parameter n comma p. We know that probability of x equal to k is n choose k, p to the power k, q to the power n minus k. Suppose you want x to the power 4. Of course you know how to do this, but let me show you an easy way. So you can keep doing this. This will give you the idea. So let me do 2 of them at a time. And then I'll do 4. So you see, I guess we can do all the 4. So this is the same as summation. K goes from, K of course goes up to n. K multiplied by K minus 1 multiplied by K minus 2 multiplied by K minus 3. The probability of x equal to k, right?
Well, S2.
Yeah, what happened to x2? All right. So that's good enough. You can do one more, but you'll get the point now. So this is probability. So you see, k equal to 0, the term will vanish. So there is no point in writing k equal to 0, right? K equal to 1, this will be, because of this terms will vanish. K equal to 2, because of this it will vanish. So this starts with k equal to 4, right, in this case. K equal to 3 also gone. So this is now k equal to 4 through n. K multiplied by k minus 1 multiplied by k minus 2 multiplied by k minus 3, n factorial, k factorial, n minus k factorial, p to the power k, q to the power n minus k. And here comes the good thing. Look here, I can cancel this. This becomes k minus 1 factorial. So I can cancel this. What do you get here? Okay. I don't know whether he had this. Do you have this in your book? Huh?
I learned it in the probability course.
All right, so now let me pull out from here n minus 1, n minus 2, n minus 3 outside. Now let's see what happens. So you have summation still k equal to 4 through n. And on the top you have n minus 4 factorial. In the denominator you have k minus 4 factorial, right? And here you have n minus k factorial. So you have p to the power n. So I'm going to pull p to the power 4 also outside. Q to the power n minus k. Now you see this can be of course written as summation. Put a new variable m. So this is m equal to 0 through n minus 4. This is m factor. And then this is n minus 4 choose m, right? P to the power m, q to the power n minus m. N minus 4 minus m, right? So what is this answer? This one? No. N choose k, p to the power k, q to the power, that's 1. So this is 1. So you get this result interestingly. So from here you should, for a binomial you have the expected value of x is, you can see np, expected value of x multiplied by x minus 1 is n multiplied by n minus 1 p squared, expected value of x multiplied by So from here itself, you see unbiased estimator for p squared is, you can see, is, our case it was t. So t multiplied by t minus 1 over n into n minus 1. This is the view, right? Which I think many of you had. But my interesting point is if you want x to the power 4, you can figure it out from here. It's much easier, right? So expected value of x squared is this plus np, right? So, and you simplify it. So for example, from here, expected value of x squared equals n into n minus 1 p squared plus expected value of x. This is np. So if you expand this, you get n squared p squared minus np squared plus np. So this is np the whole squared plus np multiplied by 1 minus p, this is q. So you get np squared plus npq, as you know, and so on, right? So similarly, you can find out x cubed, x4, etc. So if you put one more term here, there will be one more term here and p5 and so on. All right, let me show you a similar stuff with Poisson, right? So that's a good trick to compute the moments of binomial. So you want to compute this. Of course, I know you have Chen's theorem, that's easy, but I'll show you another result. So what is the answer to this? Anybody? Huh? All right, now on both the sides, let's taking derivative with respect to lambda. So what do you get? K equal to, so you get here lambda k minus 1 over k factorial equals? I'm going to take one more time derivative. So what do you get? K multiplied by k minus 1 lambda to the power k minus 2 over k factorial is what? Also e raised to lambda. So let's do one more time. Okay. So k multiplied by k minus 1, k minus 2. If I do one more time, it is k minus 3. And here you have lambda to the power. What do you have here? K minus 4, right? Equals e raised to lambda, right? E raised to lambda. Let me bring this e raised to lambda on that side. So what I'm going to do is, so I have summation k equal to 0 through infinity, k minus 1, k minus 2, k minus 3, multiplied by e raised to minus lambda, k factorial, lambda to the power k minus 4 equal to 1. So I am going to multiply on both the sides by lambda to the power 4, which I can do, right? So this becomes lambda 4 because 4 is not out of the summation. But look, this is probability of x equal to k, and this is summation x multiplied by x minus, this is k multiplied by k minus 1, k minus 2, k minus 3, k equal to 0 through infinity. So the whole left side is now, you see, expected value of x multiplied by equal to what? So you get all these results. Expected value of x is lambda from here. Expected value of x multiplied by x minus 1 is? So from here you can know that expected value of x squared is, look here, lambda squared plus lambda, as you know. So expected value of x multiplied by x minus 1 multiplied by x minus 2 is lambda cubed, etc. So this is an interesting Poisson formula also. Right, so from here you can find out the third order moment, from here you can find out the fourth order moment, right?